In this section, we will use the multiple number, half number, and the product to sum and sum to product number identities. The most commonly used multiple number identities are the double number identities. Hello, my name is Tom Atwater. Let's start with the definitions for the double number identities. Cosine of 2a is equal to cosine squared a minus sine squared a, which also can be written as 2 cosine squared a minus 1, but it also can be written as 1 minus 2 sine squared a. Now, the way that we get cosine 2a is to think about the cosine of a plus a, and then use the formula for the cosine of a plus a, which is the cosine of a times the cosine of a minus the sine of a times the sine of a. And then, of course, we know that the cosine of a times the cosine of a is cosine a squared, and the sine of a times the sine of a is the sine squared of a. Now, in terms of going from here to here, we just substitute using the Pythagorean theorem. And the same thing, from here to here, we use the Pythagorean theorem, Pythagorean identity, and substitute to come up with that. Now let's take a look at sine 2a. The sine of 2a is equal to 2 sine a cosine a. Tangent of 2a is equal to 2 tan a over 1 minus tangent squared a. Now, both the sine 2a and the tangent 2a, we could find that they're equal to those right-hand sides by applying the same idea that we did up here with cosine. That is to say, we could find the sine of a plus a, and we could find the tan of a plus a. All right, that's great. Now, let's take a look at an example in which we use these particular formulas. Use the identities to find the sine of 2 theta and find the cosine of 2 theta, given that sine of theta is equal to 2/5, and that the cosine of theta is negative. So, to do this particular problem, we are given sine theta is 2/5, and we're told that the cosine of theta is negative. The reason that that's important is that tells us that the angle for theta is got to be in either quadrants 2 or 3. But since the sine of theta is positive, it's positive 2/5, that tells us it has to be in quadrants 2 or, in quadrant 1 or 2, and therefore the only overlap between quadrants 1 and 2 and 2 and 3 is, of course, quadrant number 2. That tells us theta is in quadrant 2. To find the cosine of theta, we can use the Pythagorean theorem, which tells us that cosine squared theta is equal to 1 minus sine squared theta. And we know that sine theta is equal to 2/5. So cosine squared theta is equal to 1 minus 4/25. We have to put this over the common denominator of 25, so that we would have 25 over 25 minus 4 over 25. That's equal to 21 over 25. We take the square root of both sides. We have cosine theta is equal to the square root of 21 over 25. But again, cosine theta has to be negative, so it's the negative value of that square root. Let me simplify that one further step and write it as negative the square root of 21 over 5. So we now have both sine theta and we have cosine theta. Since we have both of them, we can now go to sine 2 theta, which is equal to 2 sine theta cosine theta. And we can plug in the correct values for each of those. Sine 2 theta is 2 times 2/5 for the sine of theta times negative square root of 21 over 5 for the cosine of theta. Let's simplify that as far as we can, and what we'll find is that the sine of 2 theta is equal to negative 4 square roots of 21 all over 25. And that's the sine of 2 theta. For cosine of 2 theta, we would use the formula that it's equal to cosine squared theta minus sine squared theta. And we have, of course, cosine theta is negative the square root of 21 over 5. Sine theta is 3/5. So that means this is equal to negative square root of 21 over 5 squared minus 2/5 squared. And I think I might have said that that was 3/5 earlier, but it is 2/5, so it's 2/5 squared. Simplifying here, of course it's going to be positive. The square root of 21 squared becomes 21, and it's all over 25. Minus 4 over 25, which gives us an answer of 17 over 25. So that's how we can use the double number identities in this particular case. But they can also be used to derive multiple number identities. In this next example, we'll find an identity, in this case, cosine of 3x, we want to write in terms of the cosine of x. We then want to support that answer graphically. So, to start this off, we would write that the cosine of 3x would be the same as the cosine of 2x plus x. And that brings us back to the identity of cosine of a plus b, and that's equal to cosine 2x cosine x minus sine 2x sine x. And now you can see where we would have to use the double number identity to replace cosine 2x. And similarly, we can replace sine 2x with its double number identity. So let's do that. In fact, let me use a slightly different color chalk so that you can see the cosine of 2x I replace with cosine squared, x minus sine squared x. And I'll put that in parentheses. Then that would be multiplied times cosine x. Then minus, well, this time I want to replace sine 2x, and I'm going to replace it with 2 sine x cosine x. Put that in a parentheses, and that's going to be multiplied times sine x. So now, let's continue this, and of course we must distribute the cosine x, which gives me cosine cubed x minus sine squared x cosine x. I must also distribute this, but there's only one term there. So I simply get minus 2, and it's sine squared x cosine x. Well, interestingly enough, we see that those two terms are exactly the same. They're both sine squared x, cosine x in terms of the variables. So I have -1 and -2 of them. So my final answer is cosine cubed x minus 3 sine squared x, sine squared x cosine x. So now what we need to do is replace sine squared with its equivalent from the Pythagorean identities of 1 minus cosine squared. So this would be equal to cosine cubed x minus parentheses 3 times 1 minus cosine squared x times cosine x. Well, now what I need to do is both distribute the 3 as well as the cosine x. So what I have now is cosine cubed x minus 3 cosine x plus 3 cosine cubed x. I see that I have a cosine cubed and a cosine cubed, so I can combine those together to give me 4 cosine cubed x minus 3 cosine x. So let me write that here. 4 cosine cubed x minus 3 cosine x. And now I've written it completely in terms of just cosine. Now what we want to do is verify this on the calculator, or at least support it on the calculator. So let's take a look at that. I've already plugged my equations into the calculator, so let's take a look. You see that on the top line I have cosine 3x, and for the equation y sub 2, I have the 4 cosine cubed x minus 3 cosine x. I hit my graph key, and there's the graph, which again means that the graphs are identical, they are overlapping. But just to prove that in terms of looking at the calculator, you can see that I've got y sub 1 is cosine 3x, and y sub 2 is the 4 cosine cubed x minus 3 cosine x. So they are, in fact, overlapping. There are identities for the product of two multiple number angles. They are the product to sum identities. Here they are. The cosine of A times cosine B will equal 1/2 the quantity cosine of A plus B plus cosine of A minus B. The sine of A times the sine of B is equal to 1/2 of the quantity cosine A minus B minus the cosine of A plus B. We also have the sine of A times the cosine of B, and that's equal to 1/2 the quantity sine of A plus B plus the sine of A minus B. Finally, we have the cosine of A times the sine of B, and that equals 1/2 the quantity sine of A plus B minus the sine of A minus B. These identities are very important identities in calculus. Let's see how to use them in this next example. Write the expression as a sum or difference of a trigonometric function. We have 2 sine of 58 degrees times the cosine of 102 degrees. So what we'll use here is the product to sum identity. Sine A cosine B equals 1/2 sine of A plus B plus sine of A minus B. So we have 1/2 the sine of 58 degrees plus 102 degrees plus the sine of 58 degrees minus 102 degrees. That's equal to 1/2 the sine of 160 degrees plus the sine of negative 44 degrees. Now, remember that our original problem was 2 times the sine of 58 times the cosine of 102. So that means I need to multiply both this side of the equation as well as this side of the equation, which means that when I multiply by 2, the 1/2 and 2 will reduce down to 1. So what I would have then is that 2 sine 58 cosine 102 is equal to, again, that's going to reduce down, and I'm going to get sine of 160 degrees. And then I want to remind you, using the negative number identities, that the sine of negative 44 is negative the sine of 44. So we find that it's equal to the sine of 160 minus the sine of 44 degrees. From these identities, we can derive another group of identities that are used to rewrite sums of trigonometric functions back into products. Here are the definitions for the sum to product identities. The sine of A plus the sine of B is equal to 2 sine of the quantity A plus B divided by 2 times cosine of A minus B divided by 2. The sine of A minus the sine of B is equal to 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. Cosine of A plus cosine of B is equal to 2 times the cosine of A plus B over 2 times the cosine of A minus B over 2. And finally, the cosine of A minus the cosine of B is equal to negative 2 times the sine of A plus B over 2 times the sine of A minus B over 2. Now, these identities are also important in calculus, so let's do an example. Write the expression as the product of two trigonometric functions. We have cosine 4x minus cosine 2x. To do this problem, we want to use the identity cosine A minus cosine B, which is equal to negative 2 sine of A plus B over 2 times sine A minus B over 2. So in particular, A is 4x and B is 2x, and therefore this would be equal to negative 2 sine 4x plus 2x over 2 times the sine of 4x minus 2x over 2. This simplifies then to negative 2 sine of 6x over 2, which is 3x, and 2x over 2, which is sine of x. Now that we have rewritten product to sums as well as sums to products, I want to give you the opportunity to rewrite an expression using these identities. Write the expression as the product of two trigonometric functions. Sine of 2 theta minus sine of 4 theta. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did on this problem. I've written out the formula that you need to use. Sine A minus sine B is equal to 2 cosine A plus B over 2 times sine A minus B over 2. In this case, A is 2 theta and B is equal to 4 theta. So this is equal to 2 cosine 2 theta plus 4 theta all over 2 times the sine of 2 theta minus 4 theta all over 2. And this simplifies then to 2 cosine, well, that's 6 theta over 2, which is 3 theta. And this is 2 theta minus 4 theta, which is negative 2 theta over 2, so it's sine of negative theta. Remember that the sine of negative theta is equal to negative the sine of theta, so we should take this one step further and say that it's equal to negative 2 cosine 3 theta times the sine of theta. I hope that's the answer that you got when you worked this problem out. Now, in the study of conic sections, we often use half-number identities. These identities are derived from the double number identities using algebra. Here are the definitions of the half-number identities. The cosine of a over 2 is equal to plus or minus the square root of the quantity 1 plus cosine a divided by 2. The sine of a divided by 2 is equal to plus or minus the square root of the entire quantity 1 minus cosine a over 2. The tangent of a over 2 is equal to plus or minus the square root of 1 minus cosine a over 1 plus cosine a. Now, the tangent of half of a is also equal to the sine of a over 1 plus cosine a. It's also equal to 1 minus cosine a all over sine of a. In terms of deriving those formulas, we said we could use the other identities to actually derive those. Let's do an example in which we will find another way to get the exact value of a trigonometric function. Use a half-number identity to find the exact value for cosine x over 2, given that the cosine of x is equal to 1/4 and x is between 0 and 2 pi. I'm sorry, between 0 and pi over 2. Now, since the x is in quadrant 1, then the half number, that is x over 2, will also be in quadrant 1. The exact value for cosine in quadrant 1 will turn out to be then positive. I have our half angle formula here that we're going to use. Cosine of a over 2 is equal to, in this case, we'll take the plus the square root of 1 plus cosine a over 2. So what we're looking for is the cosine of x over 2, and that's equal to the positive root, because it's in quadrant 1, of 1 plus the cosine of x all over 2. But we know that the cosine of x is 1/4, so it's 1 plus 1/4 all over 2. To combine the 1 and 1/4, we have to change the 1 to 4 over 4. Add to 1 over 4 gives me 5 over 4. So this will be equal to the square root of 5 over 4. And now, when you're dividing by 2, you actually multiply by 1/2. That will then give me the square root of 5/8, which, if I rationalize the denominator, gives me the multiply top and bottom by the square root of 8. So I get the square root of 40 over 8. But of course, the square root of 40 can be simplified. So the square root of 40 is equal to 2 square roots of 10. But of course, the 2 and the 8 will reduce it down, so I'll end up with the square root of 10 over 4. And then that is my answer. Great job in today's lesson. Now, in this lesson, we looked at several important identities that will be used in calculus. They are easy to learn and use if you get lots of practice doing the problems that require them in the solution. So be sure to work the exercises that your teacher assigns and have some fun, and we'll see you next time.